going to look at something that is the same as isotopes, and that is something we call nuclides. When we're talking about nuclear reactions, we call isotopes nuclides. So sometimes I'll say isotopes, sometimes I'll say nuclides. Remember, atomic number is the number of protons, mass number is the number of protons and neutrons, and we use this isotopic notation to show that. When we are looking at nuclear reactions, we have to be very concerned about the number of protons and the number of neutrons, because they're both in the nucleus and they change. So a nuclide is exactly the same thing as an isotope, and what we change though is instead of calling this the mass number, we just call it the mass, and instead of calling this the atomic number, we call it the charge, because that's there's 6 particles with charge in the nucleus, and those are the protons. So these are isotopes, and these nuclides actually have different stability. Carbon-12 is very, very stable and rarely undergoes a nuclear reaction. Carbon-13 is less stable with 7 neutrons, and carbon-14 is even less stable. When they're unstable, they're radioactive, and we call them either a radioactive isotope or a radioisotope. What happens is they spontaneously, from the nucleus, emit energy or particles. And when we talk about radioactivity, we're actually talking about the particles that are coming out of the nucleus, and it's sometimes called nuclear radiation. Of all of the known isotopes of the elements, the majority, well, many of them are unstable, but a lot of them are stable. They don't really decompose. But 300 of them will spontaneously undergo a nuclear reaction and emit either energy or particles. And then we can make some radioactive isotopes. We call them artificial isotopes. We can make them in colliders, and we use them for a lot of purposes, for instance in medicine. The radiation that comes out of the nucleus are alpha particles, beta particles, positrons, and gamma rays. And so we're going to look at these different things. An alpha particle is full of energy. It comes out of the nucleus very fast, and it has 2 protons and 2 neutrons. If you think about the periodic table, 2 protons is a helium atom. And so these alpha particles really are just a helium nucleus coming out of another nucleus. It has a positive 2 charge and a mass number of 4, so we either write alpha or we write helium with 4-2. On the alpha particle, we'll write the 4-2 also. A beta particle is just an electron. We use the symbol beta, or we'll use an E for the electron. Because an electron has no mass, the superscript is 0, and because it has a charge of -1, we put a -1 down here. What happens is, in a nucleus, when a neutron decides to become a proton, we really don't understand what controls it, but a neutron will spontaneously become a proton, and when it does, it shoots a beta particle out of the nucleus. A positron is something called an particle. It's a particle of antimatter. What is antimatter? It's really weird stuff. But a positron is a beta particle, but with a positive charge. So we call it a positive electron all the time. It uses the symbol E or the beta, and the mass, of course, is 0, but the charge is +1. We use the symbol beta, but we'll put a positive on it to indicate that it's a positron. And the way that these happen is a proton in the nucleus will spontaneously change to a neutron and spit a positron out of the nucleus. Then there are gamma rays. Gamma rays are like supercharged X-rays. You know, X-rays are really high energy and do a lot of damage to your body and other things. Gamma rays are just like X-rays, except they have even more energy. So they're like X-rays on steroids. And these come out of the nucleus also. And what happens is the nucleus is evidently in a real high energy state. And what happens is it decomposes to a lower energy state. And when it does, it shoots out this gamma ray. When they are emitted from a nucleus, there's no change in mass and no change in charge because they're just basically a particle of light. You can see there's 0 mass, 0 charge. So what you will see is the element doesn't change. You know, the number of protons hasn't changed. It stays just the same. It just has less energy. Now, radioactivity is really high energy and very damaging, but we can't detect it with our ears, nose, eyes, or anything. This will, when radioactivity hits a cell, it will damage it, sometimes to the point of killing it. Cancer cells divide rapidly, and so when you use nuclear radiation, nuclear radiation will kill cells that are dividing rapidly, and because cancer cells are dividing rapidly, you see that nuclear radiation is used to treat cancer cells. We also can shine it on food, and when we do, it kills organisms in food and it doesn't leave any radioactivity behind. So it's very effective in a way of preserving food. The penetrating power of radioactivity depends on its mass, energy, and its charge. Smaller mass and smaller charge allows the particles to go deeper. And so a beta particle has very little mass and a small charge, so it goes very deep. A gamma ray has no mass and no charge, so it goes even deeper. An alpha particle is pretty big, and so it doesn't go very deep in your tissue. So if we look at the damage that they will give, gamma rays have the most damage, then the beta and positron, and then the alpha particles. Positrons actually can be very damaging because the positrons are antimatter, and when they collide with matter, they annihilate, meaning they they cease to exist. And when a beta particle and an electron collide, 2 gamma rays are emitted, so positrons really are very damaging. When they penetrate tissue, they form free radicals because they destroy bonds. And these are really damaging and will cause a lot of changes in your DNA and proteins, and they can actually cause cancer. If you're constantly, you are constantly being exposed. The sun and the earth all are emitting small amounts of radiation all the time, but it's a small concentration. Where you really get dangerous amounts of radiation is from artificial sources, artificial isotopes that we create and then we use in various things, like medical diagnostics or medical treatments. So, just to summarize here, alpha particles penetrate the skin and that's about it. Beta particles go deeper. They'll go through your body and do damage on the way through. Gamma rays and X-rays, they go even farther. Neutrons, because they have no charge, will penetrate all of them. Will penetrate very deep. Will even go partway into concrete. Now, to measure radioactivity, we use some units. Just remember that these units are just the same as a metric base unit, and we can use prefixes with them. So a millicurie A milli is equal to 0.001, so a millicurie is just 0.001 curies. And so if you see conversions based on these, just rely on your understanding of the metric system. We do measure radioactivity that someone accumulates over time, and we use something called a REM. And for the most part, what we typically are exposed to does no damage. That's about less than 25 REMs per year. But if you get higher, you're going to start seeing problems in your body. And the reason I'm bringing this up is I want to introduce this term to you, the LD50. You'll see this in medical information. And an LD50 is a dose at which you will kill 50% of the population. So for humans, what is that? That's 500 rem. Now you get damage below that, but death of 50% of the individuals will occur at 500 rems. You'll see LD50 for medicines and for poisons, and it's the same thing. If you see LD50 equals maybe 5 grams per kilogram, well then you know that if someone gets that dose that they have about a 50% chance of living.